Hello, I am Matthew, and I'm glad to talk to you all today about pattern detection in high-dimensional data. So, over the summer, what we've been interested in is comparing similar populations that may or may not be dependent on, that may or may not have a diagnosis of opioid dependence. However, the greatest challenge we've been having this summer is getting access to the data in the first place to do analysis on. So for today, I will discuss the methodology that we plan on applying. So high-dimensional data is characterized by having many features, and these days, this kind of data is sort of collected without any sort of hypothesis to test. So it's a challenge for us to best make sense of this data. And what we're interested in is using an approach from topological data analysis, and we'll be using the map. We started by using the mapper algorithm. So what we want to do is go from our high-dimensional data to a weighted directed graph. So essentially, we're simplifying what we're looking at. And then with this graph that's easier to visualize, we can utilize optimization algorithms to discover sort of the most interesting activity, whether it's paths or branching activity. And then from there, we can look at what's the most important in our graph, and we can use that. We can analyze that. And what we want to do is find diverging subpopulation level behavior, and ultimately we want to be extracting hypotheses from this process for further predictive testing. And applications right now include plant phenomics and hospital patient trajectories. So I guess just to set the stage, you can imagine that the graph we want to get as a process, I guess like a problem, an application problem we're interested in, would be sort of following events of, say, hospital patients over time. So let me first discuss the mapper algorithm that we'll be using. So we'll start by having a bunch of filter variables. These are variables that we'll pick out from our feature space, and those will form the high-dimensional space that we'll be working with. And then we'll also be picking an output variable from this space, and I'll elaborate on that in a second. So with our space of filter variables, what we'll be doing is, with some set size, meaning set like intervals for each dimension, and overlap between each interval, we'll be partitioning this space into hyperrectangles, and in each hyperrectangle with overlap, we will be using a clustering algorithm of our choice. And so this output variable is what's used for the clustering. And again, it's something that we pick based on our application of interest. And ultimately, after the clustering, we will have a topological object that easily translates to a graph. Essentially, vertices will represent cluster centers, and edges will represent intersections between these clusters, meaning that some point matches to multiple different clusters. That'll form the edge. So once we have this graph, we can set edge weights by the following. Find averages of this output variable in each vertex, and the graph will be directed from low to high based on the difference between these values. And here is sort of a picture just briefly showing the process. Imagine this is like higher dimensional space, the space of our filter variables. And then we get a graph like this. Imagine there's arrows, meaning it's directed. So we'll have this chosen filter. For applications, say it's time. So if you go left to right, we'll be maybe following days since someone was admitted into a hospital. And ultimately, with applications like this, we might expect that we start from the stem, say like the whole population, like day 0 or something, and then we'll have these branching activities where subpopulations break off with their own behaviors. So yeah, this is what's called a flare, essentially the branching process. And so at this point with our graph, we're interested in finding what paths and flares are the most important to look at. So this just encapsulates the interesting flare algorithm. Essentially, we'll be having this backtracking process of accumulating edge weights, reaching branching nodes, and then dividing the score amongst stems. And this is something we sort of follow back to a branching node of our interest, and then that'll be a score for such a branch. And then for interesting paths, let's refer back to here when we talked about how, I guess for each cluster we picked the average and sort of took a difference, to sort of get the directions. So I guess, we could do a similar thing with filter variables. Take the average and take the difference between them, make it 1 if it's, if it's positive going this way to that way, 0 otherwise. And so what we define as an interesting path would be a path where if you follow on the directed edges, for every filter variable, you'll be monotonically increasing or decreasing. So that makes it interesting because we'll be noticing for all of our filter activity, filter variables, that we're sort of getting away from the average. So that's what makes it interesting. And then we have this interesting path equation, which applies for interesting paths and is non-linearly based off of the edge weights, again, which relates to the output variable. And so that constitutes an interesting path. So how can we find the most interesting paths in our graph? So there are different optimization algorithms. One example is max IP, which gets us the largest IFP value for some path. And so that gets us the most interesting path in our graph. And another optimization algorithm we can use is IP, which sort of partitions most or all of the graph into a set of paths, such that if you add them up, it maximizes the sum of their IFP values. So ultimately through this, we get the most interesting paths and branches. And from there, we can do analysis. So say, we have a stem and we have branching activity, etc. Say now we know the most interesting paths or interesting branches. What we can do is sort of do analysis by focusing on these vertices. For example, so I guess like with filter variables and output variable, we pick continuous valued variables. But say now if we're doing our own analysis on this graph, we can say make each vertex a pie chart or whatever we want, or like different, pick whatever outputs we're interested in, and we can do data analysis and try to learn information from this graph. And that'll ultimately help us to work on further predictive models. And that's it.